Hello everyone, good morning. Nice to see you here before 2021. Right? So today will be the last lecture in year 2020 for this course. Okay, and we will finish off the sections on the PLC and basically what we intend to cover on those topic in the book by Meneses has been covered, okay, by the end of these sections, right? Okay, so the goal for these lessons, okay, today is to achieve the outcome that you should be able to read, okay, to understand what the PLC simple PLC programs can tell, right? And then from that you may use your creativity to develop a simple PLC program based on your knowledge on programming that you have learned throughout the years, right? On today's note, programming has become not a specialized course or maybe specializations that that only certain group of people should know. Okay, it should become a handy tool for everyone. Okay, that's why learning programming has been part of the education's reviews throughout the years, okay, adopting into the primary secondary schools. Okay, so in the futures programming will become a tools, okay, instead of a specialized field, right? So you have to rethink on doing it, okay, on a regular basis. Whether you like it or not, that would be a plus point for you. Okay, so I can recall that because of I like to do programming somehow, right? So therefore I can do I learn programming language quite fast. Okay, that when I go for my study there, I just pick a language that I think would be useful, okay, because of the interface between CAD, the FEA analysis software that require Fortran, okay, and also Python, but I don't try with Python, only the Fortran, okay, in order to integrate it with in the software, okay, because we want to change the certain characteristics of the behavior of the FEA software. Okay, so it would become a handy tools, okay, that you would use it not only to process, but another important thing is to visualize, okay, because nowadays data will become more and more easily available, and you have trouble to process them. Okay, so this programming skills would be very useful. Okay, so that is part of the story, right? So back to here, okay, so today's goals would be to understand and develop the simple PLC program, okay, by learning all those should I say maybe examples. From examples, okay, you can easily grab the ideas, okay, on how to deal with it. Okay, so just a recap, last sessions we talked about the address in the internal component and the internal components of a PLC, where we have the input, output, okay, and then every part of it there is address and so on, okay, but we would not touch much on this, okay, at this beginning level. Okay, we just know that in the PLC, whenever we connect input device or an output device to a PLC, the connection point would have an address, okay, that you may refer to later on, right? So it could be I 2.5, I 1.1, okay, or Q 0.2, okay, so that would be your address when you need to do your programming, okay, to tell which particular connections or port to do the readings and to produce the output, okay. Just an introductions on the programming language for PLC, okay. It has been developed quite long time by most of the manufacturers. As you recall, we say the PLC has been there since 1960s, okay. So throughout the years there are no standards, okay, so every single I would say developers or manufacturers will produce their own way of programming the PLC, okay. So therefore, until there is a lot of different type of language exists, okay, and finally there is a IEC standards, okay, 61131-3 that have been adopted to deal specifically for a PLC, okay. So it would define the basic form of PLC, the and, or, and other things, okay. And also the programming language can be categorized into two categories. Either it is graphical type of language or a text-based language, okay. So again, this standards only is still general, okay, but it gives a guide where it should go, all right, until maybe someday there are something more innovative, then they will update the standards. Otherwise, that would be the guideline, and most of the manufacturer will start to comply with it, so that the skills of people on one particular language can be used on from one manufacturer can be used on the other easily, right? So only small changes that you may need to modify, okay, to the program that you have developed, right? The idea behind it is still the same. You have to start with the algorithms, okay, what is the input, what would be the output, okay, and do the summations and all those operations and instructions, okay. So the major three programming language that very famous for PLC, okay, there are three. One is the ladder diagram, okay, ladder. The second one would be the instruction list, okay, or list language, okay, IL, or in other words they also call it as a Boolean language, all right. Then the third one would be the FBD, okay, function block diagram programming language, okay. So you can see that obviously the ladder and the logic diagram, okay, that similar to the functions block diagram, they are somehow graphical, okay, just like the MATLAB Simulink, all right. So it's graphical, and because of that you can easily get software to deal with all those things, okay. Whereas for another type of programming language, you can see the middle one, the instruction list, okay, IL, or the Boolean itself. It is in the form of text, okay. You just type one line, okay, and not, okay, and the target port would be input 1, okay, and okay, target not port would be I2, and so on, right? So that is the instruction list, okay, in the text form. Okay, so again, in the standard itself, IEC 61131-3 standards, they define actually 5 different approach instead of those 3 commonly used language. Okay, there are ladder diagram, there are functional diagram, then there are IL, there are structured text, and also there is a sequential functions chart, okay, SFC, which translate the transform the IL into a graph, so-called graphic way, right? To simplify the visualizations of all those texts. Okay, that's why as the computer development progress, okay, then you would see that all these things would be easily integrated, okay, into the computer, and slowly nowadays a PC will slowly being taken over by smartphone and tablet, okay, because of it's easily available, okay, instead of you have to workstations, tower, and so on, right? That limit the mobility of the control of the program. Okay, these standards have introduced the functions block that can be programmed in a non-standard language as well. Okay, instead of beside the 5 approach, you can also use the C++. Okay, that's why C++ is still a very important language that has been used throughout the years. Okay, so in many applications, C++ still very useful, and Fortran also another important language, okay, that has been used for many years. Okay, that's why they have a history, just like a PLC. Okay, it has a history. They are user based. They are code that have been implemented into hardwares long time back. Okay, so to replace them, you may need a change of hardware and other things. Okay, that's why to shift from one language to another that has been embedded into a hardware would be harder to displace. Okay, not like a program that doesn't related to hardware, then it can be easily replaced. But when it has been implemented into hardware, and that hardware has been used in the industry for daily operations, then it will be really hard to replace. Okay, you will later on when you work, you may see PCs that's still running on maybe Windows 2000. Okay, and yeah, maybe Windows 2000, and now maybe Windows 7 is also obsolete, right? But you can see that those PC are still there because the driver are still there. Okay, only supported with those versions of the OS, right? So here is a list of famous vendors, okay, or manufacturers. Okay, you can see that there are ABB, they are Rockwell, there are Siemens, there are Omron, there are Mitsubishi's, Bosch. I think they missed one also popular, Allen's. Allen's. Maybe that would be in the US market. Okay, but then every single of these manufacturer or vendors, they have their own programming software. They call it IDE. IDE is basically a development environment, okay, for a program. Okay, so we call it as an IDE. Okay, a program to program, right? Just like your C++ program. Okay, that would be a kind of IDE developed by different company. Okay, so you can see that every single of these manufacturer actually have their own software or IDE, and because of that, okay, this IEC standards are very useful, so that such that this ID itself could generate the similar type of code, okay, or maybe ladder diagram or whatever it is, okay, to meet the to be able to be connect to the hardware itself, the PLC itself, right? So you can see that each of these IDE, they support either the IEC standards, or they can output it into a C or C++ programming language, okay? So basically the PLC behind it, they are running using a C or C++ language, okay? But then because of the difficulty to program in the C or C++, therefore they come up with all this ladder diagram and so on, so that engineers can easily visualize them. Alright, so it's actually a level higher, okay, that you see the visualization instead of coding the for loop, while loop, and so on, right? So you will see that that when we come to the simple program of PLC later on, you will see that it's not longer really in the form of for loop, while loop, and so on, but then it's more on a sequence based flow of programming, okay, that you just put into that order, and then it will run, okay, and behind it they will generate the required functions to be inputted to the computer, okay, or no, sorry, the PLC. All right, again yeah, okay, this one here have been okay, yeah, okay. So now come to the PLC type of language, okay. The first one and the most popular would be the ladder diagram or ladder logic, okay. So you can see that the constructions of this ladder is still very similar to your automation circuit, okay, very similar with two lines, okay. Then we have the, how should I say, the instructions from from the start end to the end of the logic, okay. So you will put the sequence in terms of symbols. All right, so this symbols itself, okay, we use symbols, okay, to represent the maybe the switch or the relays, okay. But then you will notice that the flow is always from the start going to the end, right? So there is only one way flow, okay. And then along this flow you would also see that there is multiple input. They may be multiple inputs, but for the output usually you only have one output, okay. Just like in your automations circuit, you usually only have one coil to control, okay, for every single line, okay. So that would be the recommended way of doing it, okay. But for the flow of the program, there is only one way, okay. So in this ladder logic diagram itself, okay, you will see that the logics will start from here going through each of these, okay. So you will see that the address or the locations of the port to be processed would be stated up there, okay. So you may put as like this one is I1, then I2, okay, then comes to the output port of O1, right? So these are the instructions before if all this give the final finding as true, okay, then the output will be energized, okay, with the true value, right? If the output, because these are the logic, okay, you have the AND or operations behind it, okay. So if all this at the end, when it comes to an end, that it gives us a value of false or 0, then they will not energize the output. Okay, so some of the PLC today they have implemented the so-called maybe smart part, okay, of it, okay, such that the PLC itself, when they detect along this line, and when they do all the operations, since they are in series, okay, they will know at which point when they generate a 0, so whatever happens after that would be you give us a 0, right? Okay, so in that case, when they do an operations until one point they get 0, then they will skip and tells the output to produce 0 output. Okay, so that so-called somehow smart PLCs. Okay, they start to be manufactured and yeah, available today. All right, but the traditional one, they will do all this sequence. Okay, no matter you get one okay, one and one, then you get somehow in the middle you get 0, then they will still continue. Okay, even though the end you will expect a 0 output, right? So that is the difference between the smart and the so-called non-smart PLC, right? Okay, right, so again, this one we call it as a rung or network. Okay, so this branch itself we call it as rung or network. Okay, and then you may have multiple rung that's eventually we form like a ladder. Okay, that's why we call this as a ladder logic diagram. Okay, so the language may consist of symbols and all the functions such as timer and others necessary operations. So you may try to play around with it, okay, through this I found these simulators online, okay, so that you don't need to install any of the software for time being. Okay, I try to search for a suitable software, but then I realized most of them they need license, and the size is very big, and once you download it, some of them they allows like a academic license or student license. You need to register, then I don't know how long you can use it. Okay, so to be safe, okay, I just recommend a web-based simulator. It may looks like this. Okay, feeders. Okay, so what you would do here is very simple. Okay, you can type whatever parameters that you want. Okay, either it is Boolean type, numbers type, time, or counter. This like you do a programming, you declare your variables. Okay, so you may declare and add. Okay, so you will come over here. Okay, then here is the graphical part where you can drag and drop. All right, so let's say this one on. Okay, so you can see that when I press the start button on, okay, then eventually my motor will turn on. Okay, so you can see that the motor how should I say, the motor operations has been energized. Okay, once I press the stop, then you can see that the motor have turned off. Okay, so even though now I press the start button, my motor will not turn on until I reset, or so-called press again my stop button, then it will operate again. All right, so this is how you can simulate and test your program. That's why this kind of ladder PLC diagrams would be useful. Okay, then maybe let's say we want to add another one. Let's say okay, let's say we try to simulate these situations where we use a timer. Okay, then what you need to do is we add maybe just follow. Okay, to avoid delay. Okay? So this would be a timer. Okay, timer. Okay, so we add a timer there. Okay, but then your timer is not here, so what we can do is maybe you can bring the motor here. Okay, so that you may have a contact, okay, that related to your timer. Okay, so this contact will relate to your timer. Okay, so you select your, now you will have your timers conditions. You may have end or take time, okay, and the queue, right? So you just play around with it. Okay, so here I just use the queue. Okay, then since this line, no matter how it change, it may not activate my motor, so I may need to actually add my timer. So this would be on delay, right? Just drag until you see the rank turns on with the color. So you can see that output would be one side, input will be on the other side, right? So select again, this is related to this coil. Then yeah, that's it. So let's try with I changed my timer time, let's say 5. Sorry, 5. This ACC is their on. I should only set here. Okay, so never mind. Okay, I guess let's try. Okay, reset. Okay, so when I press, you can see the timer actually counting. Motor still off until it reach 5 seconds. Okay, then it will start turn on, right? So you just play around with it. Okay, so this is the counter. So for sure they will overshoot a little bit. Okay, depends on the performance of your PLC, right? Okay, so you can try that, right, later on. Okay, there are others variables that you can play around as well. Next would be the functions block diagram. This functions block diagram, as you can see, is again very straightforward. Okay, very straightforward. We have different names on it. Okay, we call it as a logic component language, or logic diagram language, okay, or logic gate language. Okay, so this function block diagram may suit those people in the electronic field, right? Because they always deal with all this block, okay, the AND block, okay, and multiple additionals of block. Okay, so you can simulate all these things again, just like a simulink. You just drag the lines and so on to simulate what is the possible output, okay, when you do the control of it, right? Again, very important things, data is transferred from, we always use left to right, okay, from one side to the other, so that when we present this diagram to anyone, people will not read in the reverse directions. Okay, it was always from left to the right. Okay, one way of directions. Okay, so say, yeah, okay, so mainly suitable for digital type of situations. Okay, then the next one would be the Boolean's language, or the instruction list. Okay, so in this instruction list, it is very straightforward. We just give the, remember in the ladder diagram itself, we have each of these block, okay, one by one, right? So each of this block will actually do certain operations. Okay, and it will start with an AND operation, so nothing and something, you get certain things, right? So therefore in this instruction list, is just a combinations. Instead of using a graphical way, it's in the form of a list. Okay, so you put the functions or the operations at the beginning, then you put a space and your output. Very straightforward, right? So we call this as operations, then this operands or your variable. So you would somehow end up like this: A, then I1, right? Meaning to say you do an AND operation, okay, starting with this variable I1. Okay, then the next one maybe you can put an A2. So the PLC will do an operations like doing A1 and A2. Okay, whether they give us how should I say, a true or false result, then they later on they will output it to your output. So you will put an equal sign to your output, right? Okay, so here is again the list of instructions list, okay, available. Again, still they are different, okay, between manufacturer, okay, still different somehow, but then the divergence of the variations have been minimized, okay, with the existing of this standards itself. All right, so you can see that for, let's say, by Mitsubishi, Omron, and Siemens, the operations are somehow different, okay, according to the standards. All right, so eventually we don't know which one is the standard. Okay, just make sure it works according to the brand that you are dealing with. Okay, so yeah, so this type of instruction lists are very useful, and many engineers, if they deal with PLC programming long enough, then they may skip the ladder diagram. They will just read this because in their mind they will see the ladder here, right? So this is the operations LD or the starting. Okay, then they do an operation with n input. Okay, so they will do an n input, then the output is outputted to this Q1. Then the next one again after this, then the next operations will be this one. Okay, doing an all operations with input IO.5. okay, then the result we output it to determine whether we should energize or not energize the connections at Q0.1. okay, so very straightforward, right? Then for the structured text, then this would be something like the C language. Okay, something like a C language. You form the bracket, if, or, and so on, right? So that would be on the more complex operations that you may need. Okay, but then again you need to see whether the PLC able to support or not. All right, so some PLC may not be able to support because of the limitations of the memory behind the PLC itself, right? So the PLC are mainly built to run at the optimized environment, so they try to minimize the functions that has been built into the chip itself. Okay, so it depends on the PLC that you are going to use here. Okay, so same thing for the sequential function chart. All right, so you may do it visually on the software, but when we translate it to the program that you intend to input to the PLC, then you have to see whether the translation is correct or not. Okay, so these are mainly based on the graphical collections of those instruction lists. Okay, and each of these would have their instruction list, right? So yeah, you will see step 1 what they do, and what kind of actions in the instruction list or maybe ladder program. Okay, ladder program to to somehow run the whole operations. Okay, so here is the summary of the three common language that has been used, okay, in the PLC, and this table are available from the text analysis, right? So you can see the code and the equivalent symbols, okay, on three different type of language. Okay, yeah, you can see different type of language, so that would be how you want to explore, depends on your needs, right? So come to the structural programming. So once we start to play around with the simple one, then now we have this what we call a structural programming, that's define the name, right? So this is very similar to the C++, or maybe you are now playing around with Arduino, okay, Arduino, then you would see that they will just use very similar terms because they are still programming language, okay. This one just to ease the communications between the engineer itself. So what it means by functions, what it means by function block, and what it means by program, right? So you can see that functions is referring to I could say still call it as a block, okay, that consists of multiple input but only a single output. The examples would be an AND functions, OR functions, and ADD functions, and so on, right? So this kind of functions already exist in most of the IDE or the program itself, right? So you may never think of how they run it, right? Unless you think that the functions that they provide is not good enough. For example, in the C language, you start with include stdio.h, right, if I recall correctly, okay. So you need to include that one. In Arduino, you also include certain libraries, so those libraries actually contain all these basic functions, okay. Unless you intend to create your own functions, then that would be what they call as functions, right? Then also, if we deal with a block where there is a multiple input and multiple output, okay, for example, it's timer, counter, flip-flop, okay, that may be not as straightforward as the function itself, okay. So therefore these function blocks will apply, okay, many of these basic function in it, okay, to achieve this multi-input multi-output operations or instructions, right? So you will start from a very basic functions, come to a function blocks, and using all these function blocks and functions together, we will form our program, right? So that is the idea or concept of the structural programming, okay. So you will see the layers behind it, right? So in the programming language, if possible, in C or Arduino, you may use include, okay, to use the library, okay. Even Android or Xcode, yeah, you still have a lot of library, okay, and there are many library in the online database as well, right? Developed by interested programmer, so you are feel free to use it, but yeah, that is the risk of it, okay. But for the PLC, it's very straightforward, okay. They don't have much of this fancy functions, okay. They're very straightforward, therefore you may not see many library exist, okay, except those basic logic operations, right? Now come to the basic PLC program, all right? We may not go into detail of this, okay, just an idea of what are the main tasks when we start programming for PLC, okay. So first thing first, since we are dealing with the hardware, okay, we grab all those input and output the signal to the output port or connections, right? So therefore first we need to configure and set up our PLC, right? So configure and set up the PLC, which one we want to connect and so on, and then those IDE given by the manufacturers, okay, they need license, you need to pay as well, alright. Those would communicate directly to the hardware, right? So you may need to configure that first, okay. But once you have configured that, then only your program will work, okay. Whatever you write, you can actually send it or sync it to the PLC, okay. So it require two steps. First, you set up the PLC and connect it to your programming tools, your PC or whatever it is, right? Then only you send it to, you can able to program, right, the logic of the PLC, okay. So here we may use a terms called a result of a logic operation, RLO, to actually tells us what is the immediate or intermediate logic output, okay, at certain point, okay. Because for example, in the ladder diagram, you may see that one block, okay, then the second one may be an N block again, okay. So N and N, so they will start to do an operation. So after one block, what is the result? After another block, what is the result? So we will call that as a RLO, okay, to terms all these immediate result after each of the block, okay. So these terms are used because as an engineer, we want to troubleshoot as well, okay. We want to see the flow, whether it's correct or not. So the changes of this signal after every single block or operations or instruction itself would be crucial sometimes, alright. So we use this RLO, okay, to characterize the logic result, okay, being created by the CPU after the blocks or maybe the cycle of the scanning, right? So again, the type of instructions can be various, okay. It's formed from the basic Boolean logic instructions, and or not and others. Then after that we have the activations instructions, very simple, logical 1 and 0, okay, with the equal sign, okay, being assigned with the equal signs. Then also we have other complements instructions, okay. This one would be more on the slightly more complex, not only logical part, okay. You may have the counting, okay, counting instructions, CU, CD, comparisons instructions, load transfer instructions would be dealing of the memory. You want to save certain information to your PLC. For example, you're doing a logging, okay. So what time, okay, it started, okay. So you have to load and transfer the instructions, or maybe sometimes you have certain program already inside, you want to load it, run it, okay, then transfer the results and so on. So that is the things that you may play around with, right? Again, in the ladder language, you may have two way of executions, or two directions of executions in the ladder language, okay. The scanning and the executions can be either in series or in parallel. So you will see that since the scanning is in it's quite fast in milliseconds. That's why they exist these two type of directions. So the first one will be series. They will go by rank. Okay, so first rank finish, then they will execute second rank, third rank, fourth rank, and so on. Okay, until the end. Whereas for the parallel executions, the PLC will start to scan first, then scan this first, third, fourth until the end, then they will scan the second one. So it seems like in the column way. Okay, we call it as a parallel executions, right? So once you get all this result, they will output, okay, according to the rank itself, okay, and output it, right? So because of the directions of the executions in the ladder diagram language itself, it will affect the result of logic order, okay, output the RLO. Okay, so we just have this simple examples here to illustrate that. Alright, so now we have exactly the same ladder diagram. The only thing is this one will run in the series executions. Okay, so this one will move here, here, then here, here. Right, this one will go in these directions. Okay, so once now let's say we energize one IO.0, right? So when this energize, initially this is open, so when we energize it, we will get the RLO after this is 1. So once we get 1 here, then this one will be energized, right? So because of this being energized, so now come to rank 2, this will have a signal of 1 since it's energized, right? So this would have a signal of 1, okay, and this one will be energized as well. So at the first scan, the output would be 1 and 1, right? Then for the second cycle of the scan, you will get 1 1 as well, right? Let's say if we do it in a parallel way, so once we start with the IOO 0.0 for this, we energize it, we get 1, but then in the parallel way, this is still 0, okay, because we haven't energized this, okay, it goes in this direction, therefore we will get this is 0. So when we comes to here, only we turn it into 1, right? So at first scan, this one will turn into 1, but come to here, initially, remember, we come in this way, this one is still 0, therefore the output is still 0. So on the first scan, we still get 1 0, but for the second cycle, the output would be now same, right? So you can see that the directions will affect mainly on maybe the first scan, okay, then after that, after they somehow regulate for some times, then everything would be fine. Okay, now yeah, again, very important message here would be, in the ladder diagram there is no reverse directions, okay, as we have seen in the automation circuit. Okay, automation circuit, we use our intelligence to find the road, right? You will go here, it can go here. So when from this point, the power or the current will flow in these directions and flow in this way. Okay, so it's actually flowing back. Okay, if we just translate this into a laddered program, then this would not works. Okay, this one will not works. Okay, it will only flow in these directions. Okay, in from left to right. Right, so in order to achieve this automation circuits output, okay, we have to use our intelligence to find all the possible roads. That's all. Okay, very simple. So we will see that from this to the F, okay, there is one road through A, B, C, F. Okay, so through A, B, C. Then second road will be A, go here, D, K, F. Okay, A, D, K, then we reach F. Then the third one would be E, DBCF, okay, EDBC, okay, and then the next one will be EKF, okay, EK, right? So by having all these possible combinations of route, then therefore we can easily form our PLC program, okay, just combinations of this, okay, just we have this, next, okay, we get this, right? So we just input it into this way, right? All the possible routes, and they are in parallel, okay, before we output it to the F. So any changes of all these combinations, we would be able to activate the coil F, okay, or the whatever it is at the F, okay, output it to the F, right? So this is the change in the idea from the automation circuit to the ladder diagram, or the ladder diagram, okay, or ladder program. Also in the Boolean instructions, okay, Boolean's instructions, or the IL language, alright, so we have the operations and the variable, right? So sometimes you may just skip this variable. So what it means by doing this one is that they will do this AND operations, okay, this and this, okay, and this all will all do this operation. So this and this, so eventually it is equivalent to adding this all line over here, okay. So this and this, okay, or this and this, right? So this is how it would looks like, right? Then also if we want to use all operations, it's just all, right? So all operations, okay. So very straightforward, right? No need to type C in or C out, okay, or then bracket all those parameters. Is very straightforward. Operation port, okay, that is the way of the PLC, right? Then the next one would be implementations of PLC and the PLC program, right? I saw Stanley have some questions. EDBK routes acceptable since cannot allow. Okay. For this, yes, okay, because we want to achieve this automation circuits, the output of this automation circuit. So we want to find all the possible routes, okay. But when we do the programming in the ladder diagram, then we cannot reverse the direction. Okay, that's why we have to find these routes. Okay, sorry, not this one. We refer to this route. Okay, to form EDBK. Okay, over here. Alright, so this ladder diagram will give us the same output with this automation circuit, right? In automation circuit, it can go everywhere they like, okay, as long as they are connected to the neutral line and the rated voltage, right? But in the ladder program, only one directions, right? So we have to find all the routes, okay, to reach from this start of the logic to the end of the logic, right? So I hope that's clear for you. Okay, next would be the implementations. All right, so here it comes to how we would want to implement it now, right? So that would be first thing first, you have to get the PLC, right? Meaning to say you need to know how many input ports you have, how many output ports you have in your PLC, and their corresponding address, right? So once you have this PLC, next would be how you want to connect it, okay? So if you may have a switch okay, normally open or normally closed, okay, and then input, it will go to the current will flow to this neutral line, right? For the outputs, they will be the same, right? So they will go from the output port, okay, to the neutral line, all right? So they will have two separate so-called circuit, right, in between them. So now if we have this type of constructions, okay, if we have this type of constructions, what happens is that this is similar to this type of ladder diagram. It's normally open switch, even this is a physical switch, and this is the program inside the PLC, okay. You have to understand the difference, right? So this is normally open and this is the input, so we have to read this RLO together, right? So together in the sense that what happened now, okay, in the initial conditions, in these initial conditions, if our program is programmed in this way, this is open and we get 0 over here, okay, as the input to I 0.1, then our RLO would be 0, okay. However, if inside the PLC our program is not programmed, okay, this not programmed, then therefore the output now would be, this is 0, go into the program, 0, not 0, you get 1, therefore the RLO would be 1, okay. So you have to read this together, right? Similar to this case, this is a normally closed switch, right? So at this state, let's say at this state itself, okay, if our program is in this way, therefore we get a signal 1 over here, so 1 to this, then this one will give us a RLO of 1, whereas if we put 1 over here, then this will give us 0, right? Then next would be the connections, okay, of the how we interpret the input just now and how it would be at the output, okay. So conventionally in our automation circuits, we have this going through a sensor, then this is our output, right? So what we will do now, we will separate them, okay, with PLC over here. So in your automation circuit, you may have various connections here and there, right? And that can be actually being programmed by the PLC, okay, to replace all this wiring in between, okay. But since this is very straightforward, basically you don't need a PLC, right, in real, but then it may not as simple as this normally, right? So you may have this sensor switch over here, just connect it, because that would be our input, whether the sensors is energized or not energized, okay. And here is our outputs, we just put it over here, right? So it's connected to the power and also connected to the power, right? So usually this one we connect to the 0 so that this is not activated, okay. We don't want this 24 volts to activate it, okay, the current flow in this coil, okay. So first we have to identify the input output, okay, and connect it to our PLC. You need to draw this, right? Then with reference to this PLC connections now, okay, you can write your program, whether it's a ladder diagram, ladder program, or IL program, the Boolean's program. So in this case, we will start with an AND operators, okay, to the input I 1.2, okay, and we output this to Q 0.2, right? Q 0.2. So this would be the address. Okay, so you have to map it correctly, right? So once we implement this program over here, then it will give us the signal exactly the same with this. Okay, when we close this sensor, okay, so when we close this sensor, this coil C will be energized. So when we close this sensor, this one will give us 1 and it will be outputted to the Q 0.2, okay, which outputted to the coil C. Okay, so that is the way of how we can start our input-output device connections for the implementations of the PLC. Right? Now we will see more examples that we have gone through previously in the automation circuit sections or the chapters. Okay, we will see the conventional start-stop operations or a machine with a self-latching situations, right? So once we press the start, okay, how it will looks like, right? So I believe this one just now you already see it in the PLC Fidel's examples, right? Very similar, right? So what we need to do is, first thing, we have to convert into the PLC implementations. Okay, it can be implemented either way, depends on the switch that you want to use. Okay, this one we may use a normally closed and one normally open. This circuit we may use both normally open switch, right? But once we connect this, the rest is how we going to program the PLC to achieve the exact same output with this automation circuit, right? So just go through this quickly, right? So let's say for this, normally this situation or this circuit, okay, this one you can refer later on. So in this stop, okay, start, so you can see the physical buttons. Now we separate it, okay, but then this additional relationship or wiring that's related to the C, we can program it. Okay, this is not really a physical button that we use. We need a human or user to interact, right? So the button that we need human to interact is the start and the stop button, so we will put it over here, right? So the rest, the wiring that we don't need the human to deal with, we will do it or replace it with a program, right? So in this program now, if we this one stop is normally, how should I say, normally closed, right? And it's connected to I 1.0, so I 1.0 normally closed, okay, normally closed. Then this one is start, right? Then when we press this one, normally open, okay, normally open. Then we can grab this signal to replace this C, okay, so we grab this signal to replace this C over here. Okay, so did I reverse the things? Let's check. I think I reversed this diagram, sorry. Alright, so this should be reversed, right? So let's say this is the correct diagram, right? So once this one is normally closed, right? So this will give us an RLO of 1, okay, at these situations. Okay, so once it reach here, then it depends on whether we press the start button or not. Well, if we press the start button, then it will on and it will turn these options on as well. Even though we release this start now, it will continue to flow, right? So sorry for that, just switch these two diagram as well as this IL together, right? So this AN is N not, okay, represent this, right? So just switch it. Okay, so that is how we can replace the automations circuit with PLC program, right? Then another examples would be the operations of relay C when the sensor switch S1 is open, right? So here again, this is connected, right? They are related to turn on C. Okay, in the automation circuit, you see that we need a sensor to control one maybe lower powered relay, okay, to switch this on and off, right, in order to control a higher power equipment, okay, because we are dealing with the small voltage of a sensor. You don't need a high power if this motor is a high power or high voltage, right? So in automation circuit, you may have this kind of diagram, but then eventually when we replace it with a PLC, you can skip this step, okay, because PLC itself, they already separate the so-called you already separate the circuit itself, okay, so you can operate it independently, okay, not directly connected anymore, right? So the sensors now will be detected based on this point, okay, so you put the sensors, just replace it, okay, and internally you don't need this D anymore, okay, you just replace it with your program, right? So you can simplify this directly into this, okay, so this is an and not, okay, normally open type, okay, so you can see that this one open, this one is closed, so it's an and not operations, right? So once you close it, this one will switch out, okay, open, right? So it's an and not operations, okay, so you can replace it with this kind of implementations, very convenient, right? Once we have a more complex program, right, so you may have 3 buttons to control different coil, okay, let's say you have this just use 3 buttons, okay, this one on, this one open, close, open, right, this one close, open, close, okay, so these 3 switch, okay, once you close it, then you will operate this one. When you close the other 2, then you will only operate this one, right? So this is how we can do the program directly into the PLC itself, okay. We have a conflicting logics over here, okay, we just have to replace it with the program, okay. So since this switch only 1, 2, 3, so we only use 1, 2 and 3, okay, so we use you can pick any one that you like, okay, you may start with this, okay, or you may start with this, right? So since this is the first one, easier to visualize, so we just take this one, normally open, normally close, normally open, right? Then connect to your PLC, you can connect to this one or anywhere you like, right, as long as your program are written accordingly, right? So next is your output, okay, so again output, you have C1, C2, C3, so just connect anywhere you like as long as the address is correct at the end of your program, right? So how we would program it is that at this state, and this state, when all of these are switch on, okay, when all of these are this one close, this one closed, okay, then C1 will operate, your C1 will operate, right? So meaning to say all of this must be closed in order for C1 to operate, Okay, so what happened is that now this and this, they are complement, okay, to each other, right? So once this one is off, this one is closed, this one will open, this one is open, then this one is closed, right, and so on. So you may eventually what happens is that when we translate this directly, it is an and not operations for all these signal. Okay, so direct conflicting of it. Okay, so you write the program as and not for all this signal, and once this one correct, okay, then we will give this signal to the output of Q 0.2 and Q 0.4. okay, and this PE is the end of the program, right? So this is how you can do your program, right, accordingly. Then next one would be the parallel branches. Again, parallel branches, similarly, you just in PLC you may not use if you want, you can still use as in the form of how should I say, you arrange S1, S2, S3 in the line if you want, okay, but that would not be recommended because we would want to use every single of this, okay, somehow, and let the program, okay, to detect how they are connected, right? So that is the idea, okay. So that's why even though they are connected in series and then in the parallel, but in your PLC implementation you just put into like every single switch, okay, you just put accordingly, okay, to the state that you intend to, okay, initial state that you intend to, right? So once you have that, then this is your output, right? So now what we do is that everything, the wiring would be done through the program. So let's see this line, okay, or this route. So this S1, S2 and S3, okay, when this initial state is the same, then what we need to do is just to combine this signal together. So A for these three signals, okay, 1.0, 1.2 and 1.4, right? Then for the next one, another parallel line, then we put OR, okay, or another line, okay, or this one again, they are connected in series, okay, so connected in series we add as an AND operators, okay. So throughout this, any output that gives us true value or logical equals to 1, then we will activate the output at Q0.3. So this numbering or address or variable must be correct, okay, according to your PLC implementations, right? Okay, then another one would be, I think this one we have gone through. Yeah, we have gone through that, okay. Another one would be permanent activations and deactivations of variables, okay. So again, some of the situation is that you want to activate, so-called activate permanently, okay, you store the state of it, okay, or deactivate permanently. So there is a conventional one, there is a specific or specialized latch or relay to deal with that, okay. It's called a latching relay, okay. It will take two input and one output. So one is set and one input is reset, okay. So once you press set, then you will permanently set until you press the reset, okay. So this actually can be replaced by your conventional latching automations, right? Conventional latching operations. So eventually you can replace it and simplify this. Okay, still two switch, okay, but you just replace with your conventional. Eventually this one is exactly the same with your conventional, except the program itself now you will designate that there is S and R, right? So in the PLC program they also support this functions programmatically in the form of S and R. S is set, R is reset. Okay, so once you have this signal, then once it is close, okay, they receive a signal or RLO equals to 1, then it will permanently activated, okay, until you reset it, okay, then it will reset and turn it off, right? So that is the beauty of the PLC. Okay, there are a lot of functions. Okay, you can also try with other examples, okay, available in the text, okay, by Manasys, okay, that will deal with timer, counter, up, down, and so on, right? So that we will not cover on that. Okay, our intention is just to let you have a basic idea of how it operates. You may start to understand, then from that onwards, hopefully when you really need it, then you can start to explore, okay, further what are the additional features that you can do, right? So this is another examples of start-stop circuit with holding logic. Okay, normally we just want to press and then the circuit will continue to run, right? So this is, okay, I think this one we also have covered it somehow. Yeah, we have covered this somehow. So it's just a repetitions of how it is being implemented, right? So you can see the idea is very straightforward, and you can see also the way we do the automations. They already have so-called standard way of doing things, right? So eventually you just mix and match with the required features or functions that you need to achieve your operations, right? So now come to the last part on the applications of PLC, right? You may have several, depends on your creativity. You have learned all these automations, how you want to control from states, convert it into automation circuit, and so on. So once you're able to convert it into automation circuit, you already success halfway. Right, the rest is how you would want to convert the automation circuit into the PLC. That's all, right? So this is an examples of how you can implement this reversing motor operations, okay, using in the automation circuit into a PLC. Okay, tracking out, okay, then you program it accordingly, okay, through this, right? Then another one would be the elevators. Moving up elevators. Again, these elevators you may have multiple inputs. Okay, this one is the one that you may see like they will self stop, okay, when no one is using it, right? So the operations may be, it may take 40 seconds, okay, as long as the photo cell doesn't detect any new people or any object passing through it for more than 40 seconds, okay, then it will stop, okay, otherwise it will be turned on, right? But then you will see that there is a M3.0, M4.0. they are related to the state of the motor, okay. Maybe they have a level 1, level 2, level 3 of the motor state, okay. From beginning you cannot exactly give the fast accelerations and so on. So there is a sequence between them, right? So you will operate what type of operations required being sent to the motor, okay, according to the coil connections, right? So this is how you can implement it. Then the next one would be another examples of layout separating object, okay, which separates object based on the height. Okay, so you have two sensors here. Okay, once B goes through, it activate these two photo cells, then it will go to this pneumatic system will push it to B so that it will go to B, right? Whereas when A pass through, this one will not activate, only PC1 will be activated, then it will switch positions to A, right? Otherwise, after some times over here, okay, after some times you may want that maybe certain object that doesn't reach certain height, okay, then what happened is maybe some debris or whatever letter that you put there, okay, so this one on the safe side, it will push it over C, okay, everything go through C, okay, except when you have this certain orientations or somehow orientations that you can get. Remember, this one may fall down, right? So when you fall down, the thickness may be lower than what it is, then you may want to send it to station C so that people can put it in the standway again, okay, or robot put it in the standway again, in order for you to process it according to the positions that you want, right? So this is the idea behind it, right? And this also would be your lab assignment, okay? So come to the lab now, okay? The lab, we intend to cover the automation circuits, the logic diagram, as well as the PLC program, right? So you may kickstart your assignment by looking at the examples given by the Manasys, okay? Somehow the instructions here I have modified a little bit, okay, so that you may need to figure out which line and so on that you may need to tune it, right, to meet this criteria, right? So unfortunately, because we are still in online mode, okay, actually we have this hydraulic pneumatic laboratory with workbenches, okay, on pneumatic and hydraulics. These are the hydraulics pump, okay, hydraulic pumps, okay, hydraulic benches and so on. So the equipments are actually inside. You can just put the pneumatic pistons and other push buttons and other things, okay. So since we cannot do the physical lab, then what we can do now is a virtual lab. Okay, so hopefully this would be your last virtual lab, okay, last semester, last virtual lab that you may need to do. Okay, just in a group of 3 people, okay, maximum. You can have 2 or so on, okay, so I encourage 3, okay. So what you need to do is design and draw a suitable automation circuit by showing the proper arrangement of this electro-pneumatic diagram, right? Remember, this is a two pistons, okay. You have to refer back to your previous slides, okay, how you can connect it to your air compressors, okay, and so on, right? So draw it out, okay, then you start with the automation circuit, okay. I believe this examples is there as well, okay, how you want to connect them only, right? Then from there you construct the logical states, okay, to control both the electro-pneumatic and the motor itself, okay, and finally develop this PLC program, right? So the examples given in the book is in Boolean program, if not mistaken, right? So you can choose either way, whether you want to use the ladder program or Boolean type program. Okay, so if possible, it would be great that you can simulate it, okay, to show that your program is working, right? So that would be your lab assignment, okay, to summarize what you have learned throughout this this course, okay, for many, or for 9 weeks, okay, so far, right? So the submission due dates would be on 8th of January, so you may have sufficient times throughout 3 weeks, 2 weeks, 3 weeks over here, okay? So here is the schedule that we have planned previously, okay? So submit it on 8th of January, okay? The format of the lab report is, how would I say, the format of the lab report is since this is like a assignment, you don't need to really go through in the form of equipment and so on, okay? What you need to do is you put into sections A this one, B this one, C this one, that's it, alright? And then your results and discussions, okay? So very straightforward part, right? No exact format, because no format marks will be given for this, right? Only the content. Alright, so come to this, we will end this part, okay? Yeah, so you can see that these automations can be programmed as well, okay, maybe through PLC or whatever it is, right? So before we end, just quick check with whether there is further questions that I have seen. Can we define the positions of the input outward self, or need to follow certain rules? No, you just free to pick whatever port you intend to, right? It's yours, to your choice, okay? It's your choice, right? As long as being properly labeled, okay, on all this diagram, and all this diagram as you deal with engineering, okay, later on all this diagram is a proof of how you implement it, right? So all this label is very important for reference by the operator, right? So once you have tested everything on correctly, label it in your ladder diagram properly with all those labels, then that would be the record to your client if you are the one who designed the whole systems, okay? They may need a manual or operation manual or whatever it is. That would be the proof that this is how it operates, right? So if they want to troubleshoot, it's their problem, or if they can't, then they will look for you, right? So this is the idea, okay? So I hope that answer all the questions. I think that's all for today, and here I would wish everyone Merry Christmas and also Happy New Year, okay? So I hope the new year would be a great year, okay, after a long time staying at home, right? Okay, so that's all for today, and see you again next year, right? Bye bye.